Now this also applies to sound waves as well, and chapter 17 has an example that we're going to look at from number 41, which talks about a wave that is propagating. Now this is a sound wave, so it's propagating as a compression wave through space, and it is has this sinusoidal shape. And then this is observed at t equals 0, and then at some time later, it's moved a half a wavelength down, and that's at t equals 0.005 seconds, so a relatively speedy wave. And the question is, for this one, what is the amplitude and what is the speed of the wave, and also what is the frequency of the wave? And so here we have, it's given in the figure that this is 2 millimeters right there. We notice in this that the crest to crest reading off the graph is from 2 to 8 meters, so that's a difference of 6 meters, so that gives us our wavelength. So let's go ahead and write those down. The amplitude we're reading off the graph is just 2 millimeters. The wavelength is 6 meters, and then it's also asking here for the speed. But the speed is equal to the wavelength times the frequency. So what's the frequency in this case? Well, this was a graph of position, but we know that it's moved 1/2 cycle, or it's moved half a wavelength or 1/2 cycle in the time between those two waves. So we can write down the frequency as moving 1/2 cycle in 0.005 seconds. So that's the same as 1 over 0.01 hertz, or 100 hertz. So that lets me calculate the velocity. The velocity is just going to be the wavelength, 6 meters, times the frequency, 100 hertz, which gives me a speed of 600 meters per second. And if I wanted to figure out the period, I could just take the inverse of the frequency. So it's going to be 1 over 100 seconds, which is 0.01 seconds. So looking at this seems to make sense. So for our significance that a speed with that much speed is going to have a relatively short period, because it's going to be oscillating very, very quickly, even though the wavelength is a little bit long.